Welcome to the training session on boundary forced convection. My name is Dan Bicus. Our learning objectives include how to identify boundaries utilizing new capabilities of GOES-R, and identifying convection forced by boundaries in GOES-R. Identification of boundaries will be much easier with GOES-R compared to the current GOES due to greater temporal resolution, particularly with 1-minute imagery. Also greater spatial resolution and to a lesser extent additional bands as well. During the hazardous weather testbed GOES-R JPSS spring experiment in 2016, forecasters were provided with 1-minute imagery from GOES 14 SR-SOR. A survey on usage of the 1-minute imagery regarding its impact on improving convective nowcasting and warning decision-making showed overwhelmingly very high positive impact. In the 1-minute example loop on the left, the forecasters found the 1-minute visible imagery valuable in assessing a storm to be elevated, with a storm moving away from the boundary towards a stable air mass, and thus a very limited tornado threat. Additional testimony from forecasters on use of the 1-minute imagery during the spring experiment include: it was easy to identify and track boundaries and gravity waves. I could clearly see the outflow boundary, which I then compared with the SBC mesoanalysis with. This combination would give me a high confidence to which counties should be included in a convective watch. As a proxy for GOES-R imagery, we consider the 1-minute data from the GOES 14 SR-SOR on 27 May 2015. This loop spans the period from before convective initiation, so that boundaries can be analyzed in the pre-storm environment. Then, as storms develop, outflow boundaries need to be monitored for potential interactions with other storms and/or boundaries. These interactions are key to monitor during the nowcast to warning decision-making time periods. When analyzing boundaries, it's important to keep in mind storm motion relative to the boundary to assess if the storm rides along the boundary or crosses the boundary towards a more stable air mass. When looking at this loop of 1-minute imagery, the additional imagery offers less ambiguity to what is occurring compared to coarser temporal resolution loops associated with current GOES scanning time schedules. The additional imagery provides a better contextual understanding in analyzing boundaries. The latency time on AWIPS, around 1.5 minutes, also offers an opportunity to utilize the imagery in the warning decision-making process. In this example, we see a dry line in western Kansas, approximately oriented like so, and we see multiple outflow boundaries that intersect the dry line here in western Kansas. In Texas, we see additional storms along the dry line, as well as an outflow boundary in northern Texas, with additional convection developing around it. Another type of boundary forced convection you may have to deal with is the sea breeze boundary. We will use Himawari imagery as proxy for what will be on GOES-R for this example over Indonesia. A sea breeze boundary can be seen in the 0.64 micron or band 3 imagery. In a few places, the sea breeze appears to be enhanced by either existing outflow boundaries and/or terrain. Since we're over the equator, sun glint is apparent over the middle of the image as it goes from east to west, as it goes from the ocean and inland water bodies, since these are highly reflective areas. We move on to the 0.86 micron or band 4 imagery, and notice how much easier it is to see the coastline. In band 4, vegetative surfaces have a high reflectance, and water has a relatively low reflectance. This contrast between land and water shows up more clearly than the band 3 imagery, which I'll go back to again so you can see the contrast. The band 3 imagery corresponds to the visible imagery on the current GOES. Coastal offices will benefit with sea breeze identification by making use of band 4. Here's band 13 at 10.4 microns, and this should definitely be used in low-level boundary identification, particularly at night as well, since the visible imagery can only be used during the day. This is close to the 10.7 micron band that you're accustomed to viewing with the current GOES. However, you'll be able to more readily identify boundaries with the improved spatial resolution. Not only can you identify the low-level boundaries, but also get a good estimate of how intense the convection is by looking at cloud top temperature trends. We now focus on convection over Bangladesh using the Himawari satellite as a proxy to GOES-R. Initial convection moves southward, producing an outflow boundary that initiates new convection and repeats the cycle until we see new convection going up along this outflow boundary, almost like a zipper effect. The increased spatial resolution of GOES-R, as approximated here with Himawari, will help in detecting boundary-forced convection. Another familiar band for following boundary-forced convection is the IR imagery, in this case band 13 or 10.4 microns from the Himawari satellite. Not only can the boundary be readily identified, but cloud top temperature trends can be monitored as well by noting brightness temperatures at cloud top. As for the 3 water vapor bands that will be on GOES-R, we use the Himawari imagery as proxy data. Don't expect to see outflow boundaries on channels 8 or 9, that is 6.2 or 7.0 microns respectively, which are the top and middle panels here. That's because the weighting function profile is generally higher in altitude relative to the height of the outflow boundary. If one of the water vapor bands may show outflow boundaries, it's this one down here at band 10, which is the 7.3 micron channel. The weighting function may see low enough in altitude to detect outflow boundaries at times. However, in this example, it's not evident in band 10, likely due to where the instrument sees is above the level of the outflow boundary. It's time for an interactive exercise with the 1-minute imagery. Go ahead and look at this loop for a while and analyze the various boundaries that you see. Once you understand where the boundaries are, see if you can conceptualize what will happen within the next couple hours on the resulting convection based on the boundary analysis that you do. Let me go ahead and give you a hint. There's a surface low in southeast South Dakota, and storm motion is generally towards the northeast as we have southwest flow aloft. So go ahead and analyze the various boundaries that you see. Okay, let's summarize the boundaries that we see in this 1-minute imagery. We have our surface low in southeast South Dakota with an associated cold front extending approximately like so, and a dry line that's just out ahead of it. And we also have a couple other convergence lines, one that we see right here, and then another one right here. And this one actually has some indications of convection that tries to get going and actually dissipates as it moves to the northeast. Northeast of the surface low, there's a warm front. It's oriented approximately like so. This warm front was reinforced by outflow from this convection off to the northeast, so it looks quite stable north of that. Meanwhile, to the south of the boundary, we see unstable cumulus lines, which indicate a more unstable air mass. Now let's analyze the later 1-minute visible loop to see what actually happened. East of the warm front, there was a lot of convection just east of the low, along the intersection with this boundary, actually the pair of boundaries, we get a storm that intersected. Meanwhile, further to the east, remember the other convergence line that we had been tracking right here, it intersected the warm front, and we had a storm that went up where I circled, and it stayed along the boundary, which was approximately east-northeast to west-northwest to southwest oriented, and that storm produced tornado fairly soon after convective initiation. So it was along those intersecting boundaries, and really that's the key utility of the 1-minute imagery. It allows you to see these features in so much greater detail than goes with the advanced 1-minute imagery, and also what you'll have with GOES-R, the better spatial resolution as well. In summary, identification of boundaries will be much improved in GOES-R, primarily due to greater temporal and spatial resolution, but also there will be some applications, such as the sea breeze, that can benefit from some of the additional channels.